Derivatives. Definition of a derivative. And what I really should say is, when we talk about derivatives, talk about rates of change. Specifically, this is kind of an important thing. When we talk about a rate of change, we're talking about how one thing is changing as another thing is changing. So kind of two very typical examples. Probably the most well-known example that we usually talk about is how y changes as x changes. Which, if you think about that, that's just the slope of a line, or the slope of a tangent line. Which is probably our most common interpretation of the derivative. Someone says, what's the derivative? Everyone's like, oh, it's the slope of a tangent line, which is not wrong. It's just not the only right answer. Another very common example is velocity. Velocity is how position is changing as time is changing. But I really want to emphasize that it's how one thing changes as another thing changes. That's the real key point to be aware of here. So when you're trying to find a derivative, you're just trying to find a rate of change. Often how something is changing as time is changing, but that's not the only thing. It's a frequent example. You're like, oh, how is this thing changing as time moves forward? Okay. Time is often the independent variable, but not always. So we want to build up to this a little bit, and yeah, we're going to talk about finding the slope. Let's find the slope of, what do we got here? Sure. F of x equal to the square root of x at x equals 4. So what we're going to do is we're not just going to do that right away because or at least we're pretending if we don't already have it, we don't have the tools to actually do that. Okay, we've got a function, square root of x, it looks, let's try and draw it decently well. At the point 0, 0, 1, 1, and 4, 2. So that's what it looks like. And we're trying to find the slope of the tangent line. We'd really like to know what that slope is. Well, we don't yet know what it is. What we can do, because we don't yet know how to find the slope of a line where we only have 1 point. But if we had 2 points, we could totally find the slope of a line between 2 points. So what we're going to do is we're going to look at another point on the curve, let's say over there. And I'm going to find, this is where my drawing skills might fail. We're going to find, oh, that's pretty good. I'm pretty happy about that. We're going to find the slope of that pink line. Where, let's say this point here is, and we're going to get very generic very quickly here. I'm going to call this, I know I'm looking at 4 specifically, but let's just be general and say that's x. And this here is going to be x plus h. The difference is h. And the difference in the y values is, that's going to be f of x. That's going to be f of x plus h. Hopefully people on Zoom, you guys, I feel like you can probably see kind of what's going on. I can make that a little bit better. I can make it better. 1 second. There's this big thing in the way. Sorry. We can make this a little bit better. Yeah, that does seem better, I think. Okay. So I'm going to find the slope of this secant line that goes through 2 points on the curve, as well as the difference in the y values. X plus h minus f of x. The difference in the x values, x plus h. X, which we should totally simplify as just h. And that's it. That is the slope of that line. And welcome. Thank you. Sure. So let's actually do it for this particular function. The slope of the line at the point x plus h is going to be the square root of x plus h minus the square root of x all over h. Now we could do the kind of inefficient thing and actually find the slope of the secant line through the actual point 4, 2. It's not what we really want to do. What we really want to do is find the slope of the line at just any particular point x, and then use the point we actually have. So that's the slope of this line here. But I want the slope of the green line. And so what I'm going to do is I'm going to let this point get closer and closer and closer to the green point there. And as I do that, and I don't want to draw more pictures because it's just going to look terrible, but as we do that, the slope of our secant line is going to get closer and closer and closer to the slope of the tangent line. That's really kind of the big idea, is that to find the slope of the tangent line, you take the limit of the slopes of the secant line. That's the slope of the secant line. To find the slope of the tangent line, it's going to be the limit as that point gets closer to that point. Or you could say as x plus h gets closer to x. But what we're really going to say is as h goes to 0. Because we're talking about this difference between them getting smaller and smaller and smaller. And hopefully everyone's doing it this way. Some people, I'll just point out. Well, let me write it down and then I'll point out. This is going to be the limit as h goes to 0 of x plus h minus f of x over h. And that is the slope of the tangent line. And this one thing is the slope of the secant line. But the tangent line slope is the limit of the slopes of the secant line. In this particular example, and I'm not going to use that part of the board because people on Zoom can't see it. For this particular problem, the slope of the tangent line is going to be the limit as h goes to 0 of the square root of x plus h minus the square root of x over h. Okay. What I wanted to mention is sometimes people talk about this limit definition of the derivative or the slope of the tangent line in a different way. So let me just ask all of you. Is anyone talking about the derivative of this right differentiation being the limit as like x approaches a, or maybe x naught of f of x minus f of a? Okay. All right. Has anyone talked about it that way? Okay. It's an alternative definition that is also perfectly valid. The only thing, I mean, it's not a bad definition, but what I will point out is usually doing it this way makes the algebra a lot harder. It's a lot easier to manipulate this and try and cancel out an h than it is to manipulate something like this and try and cancel an x minus a. I mean, it's not like super hard to do it this way, but it's easier to do it this way. So if you have the option, I would always encourage all of you to do it this way. But if someone really wants you to do it that way, we can talk about it. Just not right at this moment. So, how are we going to deal with this limit? Well, this is why we spent so much time. This is why we spent time talking about evaluating 0 over 0 types of limits. Because all of these limit definitions, or these slopes of tangent lines, same thing really, are going to be 0 over 0 types of limits. When you plug in 0 for h, you get the square root of x minus the square root of x, which is 0, over 0, which is a 0 over 0. So the way we're going to work with this is we're going to use our typical techniques. I know that when I have a square root plus or minus another square root, or even if it's just one square root, I'm going to multiply by the conjugate. So I'm going to multiply by square root of x plus h plus the square root of x all over the square root of x plus h. Just as an aside, before at the end of class, can someone please remind me to turn back on the projector just so I don't leave it off? I should remember, but I feel like I might forget. So, oh, also, when we're doing this, our goal always is to cancel out this h. That first h in the denominator is terrible. We want it gone. It's giving us problems. It's making us divide by 0. So our goal always is to eliminate that h in the denominator. The other h's we don't care about. They're going to go away. But this h right here is the problem. So I'm going to multiply out the things that are conjugates. What do I get in the numerator? What's the square root of x plus h minus the square root of x times the square root of x plus h plus the square root of x? Right. It's the first thing squared minus the second thing squared. The middle terms cancel out. That's the whole point of multiplying by the constant. And the denominator, or I should say, in the place where things are not conjugates, you just leave it as not multiplied out. Because you know you want to cancel this h, it's not going to do you any good to multiply it through. In the numerator, the x's cancel. Space is an issue. Yeah. So you can see down there. Yeah, you can see down there. Okay. The limit as h goes to 0 of x plus h minus x is just h over h times all the square root of x plus h plus the square root of x. These h's cancel. And you're left with a limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Finally, now that we've eliminated the h in the denominator that we needed to get rid of, the rest of the h's can just become 0. So I end up getting 1 over the square root of x plus the square root of x, which is 1 over 2 square roots of x. And if you're familiar with the power rule, you will observe that this still is following the power rule. Right? We just showed that the derivative of x to the 1/2 is 1/2 times x negative 1/2. If you're not familiar with the power rule, you're going to be eventually, so don't sweat it. All right, so we just showed that for any point on this curve, the slope of the tangent line is 1 divided by 2 times the square root of the x value. So specifically, at this point here, when x is 4, y is 2, the slope of this line is going to be 1 over the square root, 1 over 2 times the square root of 4, which is going to be 1/4. But I could use that at any point, right? If x was 9, I could find the slope there. If x was 6, or even a not nice number, if x was 7, the slope of the tangent line would be 1 over 2 root 7. So there are there's a lot of good reasons for doing it this way, but we didn't just do it at 4. Right? We totally could have said, I want to find the derivative at 4, or the slope of the tangent line at 4, by doing the limit as h approaches 0 of the square root of 4 plus h minus the square root of 4 all over h. We could have done that and done the same sort of work, and we've gotten an answer that was 1/4. The reason we don't do it this way is because it's, pun intended here, it's limiting, right? We don't get much more than just that from this. Whereas if you do it this way, you can find the slope of the tangent line at any point. Whereas doing it this way only uses the slope of the tangent line at x equal to 4. So if we have our choice, we typically want to find just the very general slope of the tangent line, or the general derivative. you don't usually want to define it at one particular point. There are some examples where we do because they're kind of weirdly defined, but for the most part, we're typically trying to find the derivative of a function as a function of x. Also, feel free to ask questions if you got them. On Zoom too. If you got questions on Zoom, you guys should ask them. Yeah.
Based on finding this slope, can we find the equation of the tangent line?
Definitely. So that's not something I frequently spend a lot of time on, but yes. So if our slope was 1/4 for that particular point, and the point was the point of 4, 2, then we can totally throw those into some I like the point slope equation. It's y minus the y coordinate equals the slope times x minus the x coordinate. And I would just leave it like that personally because I'm lazy. But if you actually want to write it just in terms of y, you have y equal to 1/4 x, and then 1/4 times -4 is -1, and we add 2, and so we get y equal to 1/4 x plus 1. That'd be the equation of the tangent line.
And to get the y value, we have to plug it in into the original.
Right, because that's yeah, definitely. Because plugging into the derivative gives you the slope. Plugging into the original equation gives you the y coordinates. Other questions? I don't want to touch my mask with charging hands. I want to drink water, so. You're leaking? All right, well, anyway. So, let's see, where did my notes go? Where did my notes go? There we are. So typically, most people are going to want you to learn, use the limit definition of the derivative to calculate some derivatives. Yes, we're going to move away from it, right? You're not going to have to do it forever, but typically on your first exam for sure, probably for sure, someone's going to ask you a question like, find the derivative of this function using the limit definition, or find the slope of a tangent line of this function using the limit definition of the derivative. So just, I'm going to say it again, well, maybe not again, but slope of the tangent line of a function is the derivative of the function at that point. And it's equal to, it's defined to be the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. And you should definitely memorize this. And really, you should think of it as just, well, this is just the slope of the secant line, and I'm just taking the limit of it. If you remember this as being like the difference in the y's over the difference in the x's, it's usually pretty easy to not make any sign mistakes. I've definitely seen people over the years that like a minus h there and a plus there or whatever. It's always got to be this way. F of x plus h and minus f of x all over h. It's just the slope between those 2 points. X comma f of x and x plus h comma f of x plus h. That's all we're finding is the slope between those 2 points and then taking the limit of it. Yeah. Okay. So, typically, we do this kind of process for, I want to say three types of functions for the most part. So you would be expected to be able to calculate this for something like a square root of something, or maybe some polynomial that's maybe degree, I would say degree 3 is usually the highest we go, although you could go really higher, or some sort of rational function like 1 over x or 1 over x squared, something like that. So let's do a couple more examples. Let's find for f of x. I feel like this color is not the best color. Let's find for f of x equal to, let's go a little bigger than that. Let's go 2x cubed minus 5x squared plus 4. Let's find the derivative of that using the limit definition. You might know the power rule. You might know what the answer is supposed to look like. Great. But if someone asks you to use the limit definition on a test, you're not going to get much credit if you don't show that work. Probably not any. And before we do that, well, not quite yet. Let's write out the limit definition. So it's going to be, whoops, let's not trip on this. Okay. So the derivative is equal to the limit, if h goes to 0, of, I like to actually just write out the definition every time. Good reminder that they know that I know what I'm doing, and I know what I'm doing. That's going to be the limit as h goes to 0 of, so f of x plus h, I'm just taking my function and subbing in x plus h wherever there's an x. It's going to be 2 times x plus h cubed times 5 times x plus h squared plus 4 minus, and this is where an important fact or piece of information, all of f of x. So all of f of x needs to live in parentheses. So we distribute the minus sign and things cancel how they should. Okay. Before we multiply this out, I want to show you a trick. A trick might be the wrong word. A pattern. I want to show you a pattern. So, how do I want to say this? Yeah, let's do it this way. There's this thing called Pascal's triangle, where you start off with ones on the sides, and then all the inner terms you get by adding the kind of two things up here. So like those two add together to give you 2, and those add together to give you 3. You can keep going in this way forever, literally. And there's some really cool patterns in this triangle. Each of these rows have what are called binomial coefficients, something called the choose function, which is really the same thing. There's all kinds of neat stuff in it. But for now, what our purpose of this is it actually tells us or shows us how you can expand x plus h to a power. X plus h to the 0th power is just 1. And exciting. X plus h to the first is, I'm going to be very, very explicit, 1x plus 1h. Or really even 1x to the first plus 1h to the first. And then x plus h squared is going to be 1 times x squared plus 2 times x to the first and h to the first plus 1 times x squared. That h squared side. Which I imagine all of you already do. Right? You know how to multiply x plus h squared. No big deal. What I want to point out though with each of these is that the coefficients are coming from the corresponding row in Pascal's triangle. And the powers are just always adding up to whatever your initial power was. And each subsequent term, the power of x becomes 1 less and the power of h becomes 1 more. And this works for any power that's a positive integer, or I guess a non-negative integer since we got 0 in there too. X plus h to the 3rd is totally going to be 1 times x cubed plus 3 times x squared times h to the 1st plus 3 times x times h squared plus 1 times h cubed. And if someone was cruel and said, tell me what x plus h to the 4th is, because I want you to do the derivative of something to the 4th, the coefficients would be 14641, and we would get x to the 4th plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4th. And it goes on. I don't think I need to say anymore. So the nice thing about this is if you're being asked to find what x plus h cubed is, instead of actually doing x plus h times x plus h times x plus h, which is not the worst thing ever. Right? X plus, I get the set, I've got the same thing over there too. Right? You could do x plus h times x squared plus 2x plus h squared. But it's just kind of a pain, right? I don't want you to spend time on doing this kind of calculation that's meant to be very, very quick and straightforward. So you can certainly do it like this, but it's easier just to remember Pascal's triangle. It's a very useful tool for this. So Now I'm going to have limit as h goes to 0 of, it's still going to be kind of lengthy here. The board is kind of blurry. Yeah, that's, I don't know if there's anything I can do to make it less blurry. I will try to write a little bit bigger. Sorry, I know it's not ideal, unfortunately. I will try to make sure that, I don't know why, it was working earlier today. I don't know why it's not working now. So we multiply this out. We're going to get x cubed plus 3x squared h plus 3x squared plus h cubed. And then, oh boy, okay, this is going to be, I picked the long one. So -5 times x squared plus 2xh plus h squared plus 4. And then distribute the minus sign. Minus 2x cubed plus 5x squared minus 4. Okay, I know this looks kind of terrible. It is a little terrible. Here's the thing to keep in mind. What's our ultimate goal? What do we want to cancel? H is the denominator. To be able to do that, all the terms in the numerator need to have an H. So it means all the terms that don't have an H need to cancel out. That's always what we're looking to make happen. All the non-H terms should cancel in the numerator. Let's see what we get. So I'm going to distribute that to m at -5. This is going to equal the limit as h goes to 0. All right, I got 2x cubed plus 6x squared h plus 6x h squared plus 2h cubed minus 5x squared minus 10xh minus 5h squared plus 4 minus 2x cubed plus 5x squared plus 4 minus 4, sorry. Okay. So now I'm just going to look for the things that don't have an H in them and see if they cancel. And again, yeah, that's hard to see all that. I don't think I can make it any better. I'll say the words though. So 2x cubed cancels with a negative 2x cubed. And negative 5x squared cancels with a positive 5x squared. And a positive 4 cancels with a negative 4. So all the things that don't have an H do cancel. And then you can either just say I'm going to divide each thing by H, or if you prefer, you can factor out an H from the top. And you say I'm going to have the limit as H goes to 0 of, so factor out an H from the top. I'm left with a 6x squared plus a 6xh plus a 2h squared minus 10x minus 5h, all divided by h. Then you can cancel this factored out h with the h in the denominator. And now we can actually evaluate the limit. Say, okay, now that I don't have to worry about dividing by 0, the rest of the h's can actually go to 0. And we get 6x squared, but we're no longer writing the limit because we're taking the limit, plus 6x times 0 plus, right? You don't really need to write all this. You can just be like, oh yeah, the terms that are multiplied by 0, they just don't appear. Minus 10x minus 5 times 0. So really it's left with 6x squared minus 10x. So that's the idea. That's how the limit definition of the derivative typically works. This example is a little terrible, but not unreasonable at all. If I were a teacher, I would have no compunction about putting this question on a test. fact, I might even think it was too easy. Because polynomials usually feel, from an instructor point of view, asking someone to find the derivative of a polynomial using the limit definition feels like an easy question. Unless you're getting to a really unless you're getting maybe like higher than a fifth power. But even that, it's not conceptually challenging. It's just a lot of writing out of stuff. Yeah. All right. Okay, and then we could ask the follow-up question. Sure, no problem. Yeah, of course. So the follow-up question is, and let's write the function again. So the function which I erased was 2x cubed minus 5x squared minus 4. What's the equation of the line tangent to f of x at the point, let's say x equal to 2. We already know what the answer, I mean, we know what the answer, but we know how to find the answer. We need the slope, which we can get easily. The slope is going to be f prime of 2, which is going to be 6 times 2 squared minus 10 times 2. Is going to be 24 minus 20. 4. And then we need a point. Well, the point is x is 2 and y is whatever the y coordinate is. So our point, we say here's our slope, and our point is 2 comma f of 2. If I plug in 2 for x here, I'm going to get 2 times 8 is 16, minus 5 times 4 is 20. Did I pick a 0 of this? I mean, it's okay that I picked a 0. It's just kind of, I didn't need to, but I did. I plug in 2, you get 2 times 8 is 16, minus 20. Oh no, I didn't. I was mistaken that the minus. Okay, not a 0. It's fine if it's fine if it is a 0. That ends up being 2 comma negative 8. So then the equation of my line, of my tangent line at that point, would be y minus negative 8 equal to my slope times x minus 2. Question?
We're using the new equation.
Say that one more time.
We're using a new function instead of the old.
This is the same function. I think it's the same function I wrote down before, unless I made a mistake.
I think it's just a +4.
Oh, was it the +4 before?
Yeah.
Oh, it was a +4. Okay, sorry about that. Yeah. No, you're right. It was a +4. Apologies. So I guess it is a 0 now. Sorry about that. Yeah. I was looking at something else. Okay. So then it would be y minus 0 equal to 4 times x minus 2. And then we would just solve for y, and we get 4x. That would be the equation of the line tangent at the point 2 comma 0. Cool. All right, let's see. Let's do one more. Yeah, we got a couple more examples, and then questions people have. Oh man, 2:55. Time flies by when you're wasting 10 minutes trying to make the thing work. Sure, let's look at one more example of this, and that's kind of what we have time for. Might as well go back over here so that hopefully people on the Zoom can see it. Anyone have a color preference? Pink, green, yellow? Like which one's the best to see? Yellow? I feel like the yellow might be the best to see too. It's like there's like a white chalk in here. Seems weird. I don't know why. All right, so let's look at one more example, which is, let's look at this function. I'm going to change it up just a little bit. Let's say it's 2x over 3x. Now I want to find the derivative of this, and maybe a tangent line somewhere. So it's going to be kind of gross. The last one was kind of gross too. Still starting off the same way though. We're only starting with the limit as h goes to 0 of f of x plus h minus f of x all over h. In this case, well, I mean, just like the other one, we're just going to do the same thing. We're going to plug in x plus h wherever we see an x. So then with the limit as h goes to 0 of 2 times x plus h divided by 3 times x plus h plus 1 minus 2x over 3x plus 1 all divided by h. Now I think this looks terrible. I don't love fractions and fractions. So when I write my next line, the first thing I'm going to do is instead, the first thing I'm going to subtract these together. I mean, to get a common denominator so I can subtract those together. But then instead of saying it's all this divided by h, I'm going to say it's all multiplied by 1 over h. Dividing by a number is the same as multiplying by its reciprocal. All right, so common denominator here is also not lovely. Almost every time, if you're doing a limit definition of derivative and you find a common denominator, it's almost always just that denominator times that denominator. There's no other good way to do it. So we're going to rewrite this. Oh boy. So the limit h goes to 0 of, so I'm going to multiply this by 3x plus 1 over 3x plus 1. We have 2 times x plus h times 3x plus 1 over, I'm also going to distribute that 3 just so we can see what it is. 3x plus 3h plus 1 times 3x plus 1. Multiplied this piece by 3x plus 1 over 3x plus 1. Minus 2x over 3x plus 1 times 3 times x plus h plus 1. Or as I would prefer to write it as 3x plus 3h plus 1. So 3x 3h plus 1 over 3x all times 1 over h. Okay, that's the culprit I want to kill. Okay, that's a little violent, sorry. That's the thing I want to cancel. Right? I want that h gone. It's a problem. So here's what I want you to see. Multiplying out the denominators here isn't going to help us do that. Right? They will never allow me to cancel the h's by simplifying them anyway. What I have to work with is the numerator. Meaning I should leave the denominator alone. So I'm going to write this as limit as h goes to 0 of, well, the denominator is just going to be this times h. 3x plus 3h plus 1 times 3x plus 1 times h. The numerator is going to be a little gross. I'm going to do some preliminary work right here just to make it not take up all the space in the world. So if I multiply out this part here, I'm going to use x times 3x, so 3x squared, x times 1, and h times 3x, so 3xh, and h times 1. And then that's going to get multiplied by 2. So what we get for this first part here is 6x squared plus 2x plus 6xh plus 2h minus 2x times all of this. So when I distribute the minus 2x to each of these terms, they're all going to end up being negative. I'm going to need a minus 2x times a 3x, which is a minus 6x squared, a minus 2x times a 3h, which is a minus 6xh, and a minus 2x times 1, which is a minus 2x. All right, that could have been worse. I mean, that's not saying a lot, but it's a little bit. So let's look at the non-h things and make them cancel. They should cancel at this point. 6x squared cancel with a negative 6x squared. What else? 2x cancel with a negative 2x. Now I know I said a thing, but sometimes you get a little bit more. It's always going to be true that the non-h terms in the numerator cancel if you've done enough work to get there. Sometimes though, things with h in them also cancel. And here, the 6xh and the negative 6xh also cancel out. It does happen sometimes. All right, so if you were trying to be kind of not using a lot of paper or a lot of space, you might then be like, oh, well, then the h over the h cancels out. Instead of writing that, because it feels kind of weird, because right, if you do kind of two different kinds of canceling in the same step, it feels like if you're like, well, do they really know what they're doing there? I would probably just be like, I'm going to go to the next step and say it's the limit as h goes to 0 of, well, I know the 2h divided by h is going to give me just the 2 in the numerator. So I'm going to have a 2 over 3x plus 3h plus 1 times 3x plus 1. And then the h goes to 0. So this last h here is 0. And 3 times 0 is 0. So I'm left with 2 over 3x plus 1 times 3x plus 1, which is 2 over 3x plus 1 quantity squared. That's our derivative.